Okay, so a little bit of review of what we've been doing. We've worked on expressing things with algebraic expressions. So if I give you something like 8 less than 5 times a number. If I use x as my missing number, how am I going to express that? Perfect, 5x minus 8. The 8 less than is telling us that 8 is being subtracted from something. So even though that's stated first, it's actually at the end of our expression. Then, of course, 5 times the number is the 5x. If I say 3 times the sum of a number and 7, how would I express that? Again, using x as the missing number. Yep, sum is addition. X plus 7 in parentheses. We put the 3 either before or after, either one. So yes. The key there is we have to have the parentheses because the sum has to be done before the multiplication. We're multiplying the sum, not either of the numbers. We're looking at evaluating expressions. I might ask you to evaluate 3p plus m squared minus d for p equals 7, m equals 3, and d equals 11. How do we do that? What do we do first? Well, 3p is going to become 3 times 7, plus m squared is going to become 3 squared, and then minus 11. And Colton's exactly right. We have to do the exponent first in our calculation, so we're going to do 3 squared, which is 9. Everything else stays the same. Then what? Do the 3 times 7 is 21. And then left to right. It's all addition and subtraction. So we do the 21 plus 9 is 30, and 30 minus 11, 19. Not so bad. Now last week, we looked at different estimating formulas for construction. One of them was the number of blocks. For a basement. Of course, this is just for the walls, obviously. To do that, we looked at the, again, we just did simple rectangles. Let's say we've got a 36-foot by 48-foot foundation. We found the lateral area of the foundation. Remember how to find the lateral area? We need the perimeter. In this case, it'll be the perimeter of the house. What's the perimeter of this house? If we add up all the sides, we get not quite that much. 168 feet. That's our perimeter. Now to do the lateral area, we need one more piece of information. Our wall height I'm going to do 8 foot 8. That's one course more than 8 feet, so that when we put in our floor, we get at least our 8 foot of head clearance. So, to find our lateral area, we do perimeter of the base, in this case the perimeter of the house, times what? 8 foot 8. And we're going to write that as 8 and 8/12 of a foot. We have to express it all in feet. So that gives us 168 times 8 and 8. What'd you get? At 1,456. Okay. Did you put 8.8 instead of 8 and 8/12? That would do it. So that is our wall area, or our lateral area. Now remember, to figure out the number of blocks that were necessary, what are the dimensions of a typical concrete block? 8 inches high and 16 inches wide. So we do 8 by 16, which is how many square inches? $128. This, of course, is in square feet, so we have to convert that. Do 128 over how many square inches are in a square foot? 144. And we reduce that. Both of those can be reduced. Well, I know they can both be reduced by 4. Let's do that first. And it looks like they can still be reduced by 4. Gives us 8/9. So one block covers 8/9 of a square foot. So to find the number of blocks, required to do the basement, we're going to take that lateral area divided by 8/9. So here that'll be the 1,456 square feet divided by 8/9 of a square foot. $1,638 is correct. Any questions? This formula here is one to remember. Lateral area divided by 8/9, get your number of blocks. Now, as we mentioned last week, we would have to go through and divide up those blocks into corner blocks, because the blocks in the corner are different. There might be spots where we need half blocks if there are windows in the basement. On one side of the window or the other, you might need half blocks in order to make the spacing come out right. So we would adjust that number that we get for those half blocks and corner blocks. We're not going to worry about that in this class. We're just getting rough numbers out there. And then, of course, you might add a waste factor that blocks get dropped. They break actually quite easily if you drop them on their side. So you're going to get a couple dozen blocks broken on the job site. Usually you add a percentage, either 10% or 15% for waste, for breakage. So you'd have to worry about that as well. Have you guys ever seen how a corner block is made, what a corner block looks like for? Okay. So if you have an 8-inch wide wall, your standard block looks something like this. Look familiar? So a corner block, instead of having the notches on the ends, would look like this. It still has the one end that's set for mortar, but it has a little bit smaller cavity, and this is set on the side, so it's to butt up on the side. That's if it's 8 inches wide. If it's any wider than 8 inches, we want the exposed part here to be 8 inches. The reason we want that to be 8 inches is because it stays modular. 8 inches and 16 inches combine to make 4-foot increments as we go across the wall. As you do your stagger stack, you guys know what I mean by stagger stack, right? If your first course block looks like this, your second course has the joint right in between, like that. Well, you need a 16-inch block here and an 8-inch block here. So your next row up, you're going to have the corner block on this side. Oops, I'll do it like this. Your corner block will be here. And the normal block will be here. That way the seams will be staggered. Anyway, we want to keep that 8-inch exposed. So let's say we have a 10-inch block. The way they make it looks like this. So you got your regular block. Your corner block is still set to butt up against that. Then you have 2 inches popping out here. This will be only 6 inches long here because it's 10 inches wide there. Well, it's so that this stays 8 inches exposed here so that it, so everything matches up. This is actually, this dimension here, from here, something a little brighter, from here down to here is actually 10 3/8 inches. The reason it's 10 3/8 is 10 inches is the width of this block. The extra 3/8 is so you can have mortar in here to seal it together. Again, that's just so you stay modular with your dimensions, so you get those 4-foot increments. In construction, we try to design almost everything on 4-foot increments. Otherwise, they do make 10-inch corner blocks that are a full 10 inches wide here instead of cut back to 8, because these are more expensive. But if you're going to do that, then you've got to adjust your dimensions so that they're modular to different sizes. That's a real pain. So if you ever get into doing the design side of houses, that's a big thing to keep in mind. You get a lot of architects out there. I've seen houses that are just silly, that have nooks like this, where here to here might be like 14 feet 8 inches. Well, that's just impractical. Actually, 14 foot 8 inches actually comes out to be modular. Let's go 14 foot 4 inches. That one's not modular. So you've got studs. They're going to have one spot where there's studs 4 inches apart, and you're going to have to cut off sheeting and waste sheeting and whatever. And this here might be, 10 foot 6 or something like that. Again, it's a weird dimension. It's not going to be modular. Or 10 foot 2 even. I've seen them do stuff that it's just wasteful. It makes it really tough for the contractor to build, and what you cut off can't be used somewhere else because it's not going to be the right size. You end up with a lot of waste when you do that. Also, by your concrete guys that do your basement hate you when you do things like that. That's why most of them, they might build the foundation, might follow the house here, and they might do the bump out, but they'll usually do something like that and let this just hang over the foundation so they don't have to, because every corner, when you're doing concrete, every corner costs you extra. So putting those extra 3 corners or 2 corners in there to do that is maybe not worth the expense. So anyway, we talked about other things. We talked about joist, but we did joist last semester, so you guys have all seen that at least once or twice. The next thing we looked at, which we've seen before, is the exterior wall studs. Exterior wall studs, NS stands for the number of studs, is 12 over the on-center spacing times the perimeter of the house plus some constant B, and we'll talk about B in a minute. So let's say our house is at 36 foot by 48 foot again. So the perimeter was 168. Yeah, you're thinking the number of the area. So the number of studs, if they are spaced 16 inches on center, which is typical for exterior walls, your studs are going to be, number of studs will be 12 over 16 times 168, plus we've got to figure out what B is. Anybody remember some of the things that went into B? Plus 2 for each corner. Remember, we have to add 1 because the formula gives you 1 at the end, but not at the beginning. So recall the second one was so that when you frame your corner, when your walls come together here, you're not left with this gap from this. When you do your sheetrocking on the inside, you're not left with this gap for your sheetrock. Put an extra stud in here so your sheetrock has something to nail to. So you put your sheetrock on, you can screw to that. Generally leave at least a 1-inch gap here so that you can shove insulation into that corner. I've seen people screw up and put them tight together, then they got to drill holes and try to have to squirt insulation in there. They can't put in fiberglass anymore because it doesn't fit. So plus 2 for each corner. How many corners are here? 4. So that's 2 times 4, which would be 8. Plus 1 for each non-modular wall. What's modular mean for a house? Again, divisible by 4. Any of these walls non-modular? No. So that's going to be 0 for that. All these walls are divisible by 4, so we're not going to add anything for that. Plus 2 for each door or window. And the reason for that is you had to have those jack studs on either side and the additional framing above and below. So let's put in some doors and windows. So the boxes are windows. Of course, the slants are doors. Total doors and windows, how many do we have? 2 doors and 6 windows. That's a total of 8. So how many are we going to add for that? 16. 8 times 2 is 16. And then we add plus 1 for each interior. They usually say interior wall partition or interior wall intersection. So we got to draw in some interior walls here. So let's just say that's it. How many interior walls do we have intersecting the exterior walls? How many spots? 5. Right there. So that'll be 5 times 1 is 5. So how many total do we have to add there? There we go. Get all of them together. 8, 16, and 5 is 29. That's correct. So that's plus 29. So the 12 over 16, just do 12 divided by 16 times 168 gives us 126. plus 29, which is 155 studs for the exterior wall. Not so bad? What's that? Yeah, there are some things I could do here. But just for fun, let's. You guys familiar with the term L, E-L-L? In L, okay, so ranch style house means just simple rectangle, and then either a simple gabled roof like that, or maybe there might be like a fake dormer over one of the doors or something like that. That still is classified as a ranch style. Strictly speaking, a ranch style roof has just a single ridge. That's all it has. But they've expanded it to allow for like a small dormer over a door or whatever. But it's still a rectangular foundation. And L is starting with the base of a ranch style house with a piece like this sticking off to the side. This piece is called the L. Let's put some dimensions on this. First, what's this dimension up here going to be? 48, good. Just the 32 plus the 16. How about over here? 36, good. Just the 12 plus the 24. Oh, let's do some interior walls here. Yeah, we'll call that good enough. Do some windows. And doors. So, lead me through estimating the exterior wall studs. (16-inch space). Let's start my formula. What am I going to start out with? 12 over 16 times, yep. What's my perimeter? Still 168, yes. When you're dealing with rectangles like this, by the way, or an L like this, the perimeter of the L is going to be the same as the perimeter of the whole rectangle if you made it a big rectangle, because this just replaces that and this replaces that. So you just have to use the two bigger dimensions, add them together, and multiply by 2 and give you the perimeter. Little shortcut for you. So let's figure out what we have to add on here. What are the things that we have to add for? What's one of the things we have to add for? Corners. How many do we add for each corner? 2 for each corner, 6 corners, so 6 times 2 is 12, correct. What else do we add for? Doors and windows. 3 and 11, does that look right to everybody? So how many per each? Times 2 gives us 28. Anything else we add for? So interior walls. There's 5 of them. How much do we add for each of those? 1. So that's 5. So 1, 2, 3, 4, 5. Yep. Now there's one other thing we add for, it just doesn't apply to this house. What's that? Non-modular. We have no non-mods here, so that's 0. So what's our total? The dimension that doesn't divide by 5 or by 4. 45. So we add 45. So 12 sixteenths, 12 divided by 16 plus 1 or times 168 is 126 plus 45 is 171 studs. Loads of fun? Sure, right? Okay, so I'm going to pause this. So if you recall, way back the beginning of last fall, when we talked about the structure of numbers, we talked about something like 274 being an abbreviation. And the full form of that number looks like this. That's 200s and 7 10s and 4 1s. Well, those place values are powers of 10. 10 to the power of 0 equals 1. 10 to the power of 1 equals 10. 10 to the power of 2 equals 100. Of course, the next place value would have been 1,000. That's 10 to the third. Then it goes up. It's just powers of 10. Now, anything to the power of 0, of course, is 1. So no matter what the base of our number system is, the 0 digit is always 1s. Well, when we write out our whole numbers like this, we could actually abbreviate it and write it, instead of writing out hundreds, we write 2 times 10 squared plus 7 times 10 plus 4. We don't need to write the 10 to the 0 or the 1s there. We just imply it if there's no place value written, that that's the 1s. If we compare that now to an algebraic number written as 5x squared plus 3x plus 8, we can see the similarities. This number, it's just a number, only the place values, instead of being 10 squared and 10 and 1s, it's x squared and x and 1s. Does that make sense? Now, there are some differences. First of all, the algebraic in a whole number, either every digit's positive or every digit's negative. A negative 239, that would be a negative 200s, and a negative 310s, and a negative 9 1s. Every digit in that's negative, or every digit's positive like it was over here. In our algebraic numbers, each digit can be positive or negative on its own. We can have 3x squared minus 7x plus 2, where only one of the digits negatives and the other two are positive. Also, in our whole numbers, in our base 10 whole numbers, we can't have any digits that are bigger than 9, otherwise we carry them over. In our algebraic numbers, we can have 7x squared plus 13x minus 42 if we want to. We're not held to those place values being, each digits being no bigger than the 10, than the 9. Now, if this were a computer science class, we would actually talk about numerical number bases other than 10. We're so used to the base 10 system that we don't realize that there are other numbers that can be used to base number system. The most common one is the number 2 for binary numbers. 0, 1, 1, 1, 1, 0, 0, 1, all those. The reason they use those is because computers, either in electronics, either it's on or it's off. So a 0 is off, a 1 is on. So that's why they think in binary numbers. you can store a binary number with a series of switches that are either electronically turned on or off. Well, with this parallel between our algebraic numbers and our whole numbers, we can look at how we can combine our algebraic numbers. First of all, something like 7x plus 9x, if I combine those, what do I get? 16x. I combine the counts, 7 plus 9 is 16, and I keep the same name of x. What if I have 3x plus 11y? Careful. When we add or subtract, we must have same name, right? So x and y can't be combined when we're adding. So that just stays 3x plus 11y. If I go up with my larger numbers like this, with the more place values, I might have 6x squared plus 9x plus 4. Now the parentheses here are not an enclosing symbol. It's just saying that's a number by itself. Plus 2x squared plus 7x plus 3. When I go to add them like that, I can set it up just like I do whole numbers. I'll rewrite my 6x squared plus 9x plus 4. And then I'll line up the columns underneath. The 2x squared will go under the 6x squared. The 7x goes under the 9x. And the 3 ones goes under the 4 ones. And we are still adding here. Now we can go left to right or right to left, but since we're used to going, starting at the end and working our way backwards, that's what we'll do here. 4 plus 3 is 7. It's positive, so we're going to put a plus there. 9x plus 7x. 16x, again, it's positive, so I'll put a plus there. 6x squared and 2x squared, 8x squared. Now, all the digits here were positive. That made it easier. Remember we said algebraic numbers could have individual digits be negative. That complicates things a little bit. We might have 3x squared minus 9x plus 2 plus 5x squared plus 5x minus 7. We're still going to set them up, lining them up, so we'll rewrite the 3x squared, negative 9x, positive 2 ones. We'll put the 5x squared under the 3x squared, the positive 5x's under the negative 9x, and the negative 7 ones under the positive 2 ones, and we're going to add. So this is why we went over these a couple weeks ago. We got to remember how to work with our negative numbers. What's 2 plus negative 7? Negative 5. Negative 9x plus positive 5x. You got negative 9 and positive 5 is negative 4, so negative 4x. 3 plus 5 is 8x squared. Good. Subtraction gets a little bit more complex, but it follows pretty much the same rules. We might have 8x squared plus 3x plus 7 minus 5x squared plus 9x plus 2. Again, we're going to rewrite them. 8x squared plus 3x plus 7. We're going to put the 5x squared under the 8x squared, the 9x under the 3x, and the 2 ones under the 7 ones. And then we're going to subtract. 7 minus 2? 5. 3x minus 9x? Negative 6x. And 8 minus 5? 3x squared. Well, we had negatives in our result there, but we didn't have any negative digits in our numbers. And when we put negative digits in our numbers, things get weird. So 3x squared minus 8x plus 2 minus 7x squared plus 9x minus 7. So once again, we'll rewrite it. 3x squared minus 8x plus 2. We'll put the 7x squared under the 3x squared, the positive 9x under the negative 8x, and the negative 7 ones under the positive 2 ones. And we are subtracting. 2 minus a negative 7. There you go. 2 minus a negative 7 becomes 2 plus 7. That is 9. Positive 9. Negative 8 minus 9. Well, it's negative 8 plus a negative 9, which is negative 17. So yes, you are correct. Negative 17x. 3x squared minus 7x squared. 3 minus 7 is negative 4x squared. Be careful with the negatives. They will, as I mentioned when we covered them last fall and when we reviewed them 2 weeks ago, the negatives will haunt you. That's probably the biggest source of mistake I see in algebraic problems is dealing with the negatives. Okay, so next let's look at multiplication. When we multiply, we combine the counts. 5 times 7 is 35, and then we also combine the names. What's x times x? X squared. Now, when we had 3x plus 8y, we couldn't do it. Can we multiply 3x times 8y? We can. When we multiply, we do not need the same name. We combine the counts. What's 3 times 8? 24, and then what's x times y? xy. Good. If we have more than one name, we might have 12x squared y to the 5th times 3x to the 4th y. First of all, this y here has a power of 1. We don't write it, but it's there. Do you remember how we combine powers? So let's do the combine the counts. 12 times 3 is 36. X squared times x to the 4th. 6th. When we multiply with exponents, we add the powers. So x to the 6th. The reason I put that 1 in there for y, so now we've got y to the 5th times y to the 1 is y to the 6th also. In your notes, I want you to try 7x to the 3rd y to the 6th times 2x squared y to the 5th. So we combine the counts. What's 7 times 2? 14. Then we can combine each name separately. X to the 3rd times x squared. X to the 5th. We add the powers. 3 plus 2 is 5. Y to the 6th times y to the 5th. Y to the 11th. Again, we add the powers. 6 plus 5 is 11. Something like this is very similar to having like 5 times 23. The way we did this, 5 times 23, was we wrote the 23, we put the 5, we'd do 5 times 3, and then 5 times 2, right? We can do the exact same thing here. Write the longer number, 7x squared plus 4x on top, and the 3x on bottom. And we multiply. What's 3x times 4x? 3 times 4 is 12. X times x? X squared. And it's positive, so we put a plus there. Then we do 3x times 7x squared is? Perfect. 21x to the 3rd. 7 times 3 is 21. X times x squared is x to the 3rd. Now this takes a little bit of space, and we have to rewrite the problem. So if you took algebra or even pre-algebra, you were taught a shortcut called distributing. To distribute, we do the same process, just backwards, and we do it kind of in the same spot here. So what's 3x times 7x squared? 21x to the third. 3x times 4x. 12 is positive, so do plus 12x squared. We can hit, yeah, that's what you were doing, yes. This is actually the full process of multiplying it out. This is a shortcut that they developed, but this is the only way most of us have ever seen how to do it, is to do the shortcut. So in your notes, I want you to try this. 4x times 3x squared minus 7x plus 2. Give you half a minute or so, then we'll go over that one. So let's take a peek here, see how you did. So we do the 4x times 3x squared gives us what? 12x to the third, good, yeah. This is x to the 1, so 1 plus 2 makes 3. 4x times, remember this is a negative 7x, gives us negative 28x squared, good. And 4x times 2, 8x. It's positive, so put a plus there, so plus 8x. Any questions on that? The next step is to look at something like this. 2x minus 5 times 4x plus, or 2x plus 5 times 4x plus 3. Now again, this is similar to our whole numbers. If we have 35 times 24, we do the 4 times 5, then the 4 times 3, then we do the 2 times 5 and the 2 times 3, correct? We do the same thing here. 2x plus 5 times 4x plus 3. What's 3 times 5? Careful. 3 times 15. It's positive, so we're going to put a plus in front of it. What's 3 times 2x? 6x. Now, just like with whole numbers, when we move over to the next digit, we leave a blank here or put in a 0. What's 4x times 5? 20x. Notice that goes under the other x. It's positive, so we put a plus in front of it. 4x times 2x? 8x squared. And now we can add this. We've got 15 plus 15. 6x and 20x makes 26x, positive, so we'll put a plus there. 8x squared is just 8x squared. That's our result. This is the full, I hate it when my pen does a delay like that, the full method of multiplying those out. Now that takes up some space and it's long. Most of you were taught a shortcut. Yeah. Probably use the acronym FOIL. Yeah. What's that? FOIL? So you do the 2x times 4x. It's the first digit of each, which is 8x squared. O stood for outside, so 2x times 3 is 6x. I stood for inside, so 5 times 4x was 20x. Now, usually you just write it like this. I typically will drop down and put it under here, so I remember to combine it with the other x. And then L stood for last, so you do the last digit of each. 5 times 3 is 15. So you've got 8x squared, 6 and 20 make 26x, and 15. Look familiar? You did another way? Oh, and you combine and you add up the 4 pieces. Yeah. That's basically this. It's a visual way of doing that. Like I said, this is the actual multiplying it out. It's the same as multiplying whole numbers. This is just a shortcut so you don't have to take up that much space and rewrite it. Division. Remember if I had something like x to the 8th divided by x to the 3rd, what did we do with the powers? Subtract them. So 8 minus 3 is 5. If I have 27, x to the 5th divided by 9, x to the 3rd. I still combine the counts. What's 27 divided by 9? 3, and then I combine the names. X to the 5th divided by x to the 3rd? X squared. Most of us have never seen division done like this, but if I have 846 divided by 2, since each digit divides evenly, I can just 2 goes into 8 how many times? 4. There's no remainder, so I don't need to worry about it. 2 goes into 4. 2. No remainder, I don't have to worry about it. 2 goes into 6. 3. Dividing by a single digit in algebraic numbers is usually the same way. So I have 24x to the 8th plus 32x to the 5th minus 16x to the 3rd over 8x squared. Just like here, I divided each digit separately. I can do the same here. What is 24x to the 8th divided by 8x squared? 3x to the 6th. Good. 24 divided by 8 is 3. X to the 8 divided by x squared. 8 minus 2 is 6. X to the 6th. How about 32x to the 5th divided by 8x squared? 4x to the 3rd. It's positive, so I put a plus there. 32 divided by 8 is 4. X to the 5th divided by x squared is x to the 3rd. And finally, negative 16x to the 3rd divided by 8x squared. Negative 2x. Good. Negative 8 divided by, or negative 16 divided by 8 is negative 2. X to the 3rd divided by x to the x squared. 3 minus 2 is 1, so x to the 1 or just x. Let's take a break. Let's start up again at 2:40. Okay, so our next step, we're going to look at, we mentioned our place values. We're going to review them for a minute here. This is the ones. What's next? Tens, hundreds, 1,000s, 10,000s, 100,000s, 1 millions, and it keeps going, right? Going the other way, of course, it's the, maybe a little shorter. Well, this is the tenths, hundredths, thousandths, 10,000ths, and 100,000ths, and it keeps going. Millions, 10 millions, and so on. Well, we mentioned that we have powers of 10. 10 to the 0 is just 1. 10 to the 1 is 10. 10 to the 2nd, or 10 squared, is 100. 10 to the 3rd is 1,000. 10 to the 4th is 10,000. 10 to the 5th is 100,000. 10 to the 6th is 1,000,000. And it keeps going. 10 to the negative 1 is 1/10. A negative power is actually reciprocal. 10 to the negative 2 is 1/100th. It's 1 over 10 to the positive 2, or 1 over 100. So as we mentioned earlier, the place values in our number system are those powers of 10. Now we often will take a number like 3,800,000, and we will abbreviate it by writing it as 3.8 million. Well, there is a way we can abbreviate it even shorter by just saying 3.8. And instead of writing out the word million, we can just put in that power of 10, 10 to the 6th. And of course, you might be looking at that, recognizing this as scientific notation. In scientific notation, all we do is we take our number, we identify the first non-zero digit. Here, that is the 3. We put the decimal point after it, like we did here, and then we name the place value of that first digit, the 10 to the 6th. So if I have 0.00072, what is the first non-zero digit there? The 7, right? So I'm putting the decimal point after it. So it's going to be 7 point, we still have the rest of the digits, the 0.2 after it. What's the 10 to the negative 4? Very good. So times 10 to the negative 4 is the place value of that digit. Now, we don't like having to write out the number, the place values every time we convert numbers in scientific notation. So what we were taught was shortcuts. Here, we kind of just started out the same. You put the decimal point after the first digit, then you move. It started here, it went 1, 2, 3, 4, 5, 6 spots. This was a big number, so that's why it's 10 to the positive 6. Here, you put the decimal after the first digit. It started out here, it went 1, 2, 3, 4 spots. That was a small number, so it's 10 to the negative 4. Make sense? Numbers that are larger than 1, of course, their place values are positive. Numbers that are smaller than 1, their place values are the negative powers of 10. So if we have 590,000 and we want to convert it into scientific notation, where's the decimal point going to go? Between the 5 and the 9. It's going to be 5.9. Decimal point started at the end of the number, so how many spaces did it move? 5 spots, and is it going to be positive or negative? Positive, because that is a large number. It's bigger than 1. So 0.000082, where is my decimal point going to go when I put that in scientific notation? Between the 8 and the 2. So my decimal goes there. It started over here. How many spots did it move? 6. Is it going to be positive or negative? It's 10 to the negative 6. This number was smaller than 1 to begin with, so it's a negative power of 10 for the place value. And of course, going the other direction, we might have 3.6 times 10 to the 7th. We write down our 3.6. Our decimal has to move how many spots? 7, whatever our power of 10 is. Now that's a positive to power 10, so this is a big number. So to make a number bigger, we move it what direction? To the right. So we go 1. Well, we're out of places, so we have to add zeros. So that'd be 2, 3, 4, 5, 6, 7. So 36 million. Or we might have 6.1 times 10 to the negative 6th. So we start out with our 6.1. How many spots do we have to move the decimal point? 6 spots, and since it's negative, this is a small number. Yeah, we move to the left to make it smaller. So we go 1, have to add zeros, 2, 3, 4, 5, 6. So this is 0.000061. Any questions? Well, there's something out there called engineering notation. Whenever you throw engineers into things, it makes things a lot simpler, right? Sure. Old joke, if anybody can complicate something, it's an engineer. Engineering notation is similar to scientific notation, only it lifts one of the restrictions. In scientific notation, we can only have one non-zero digit for the decimal point. Only one digit in front of the decimal point, and it can't be a zero, put it that way. In engineering notation, we can have 1, 2, or 3 digits in front of the decimal. What's that? Well, there's a good reason for it. It adds a restriction that's not in the scientific notation. In scientific notation, the power of 10 can be anything depending on how many decimal places we had to move. In engineering notation, the power of 10 must be a multiple of 3. So 3, 6, 9, 12, 15, or -3, -6, -9, going either way. So if I have a number like 84,300,000, and I want to put that in engineering notation, basically I have to move the decimal point 3 places at a time. So I go 1, 2, 3. Can I go 3 more? Yeah. 4, 5, 6. Can I go 3 more? No, I stopped there. So that's 84.3 is where the decimal point ended. I moved it 6 spots, positive or negative. That was a big number, so it's positive. So 10 to the positive 6. So I have 0.00027. I move my decimal point. 1, 2, 3. Can I move it 3 more? It looks like I can't, but I have to. Right now, there's only zeros in front of the decimal point if I stop there. We have to have 1, 2, or 3 digits that are not zeros. So I have to go 4 or 5, and I have to add a 0 to go 6. So that's 270 times 10 to the -6. That was a small number, so it's a negative power of 10. Why are we complicating things by restricting our power of 10 to be those multiples of 3? Well, there are a lot of applications like electronics, computer memory, stuff like that, where we use metric units, and we only use the main metric units. Like we might have a volt, we might have a millivolt, microvolt, kilovolt, or megavolt. Well, the main unit, the volt, it would be a volt or an amp or an ohm. These same prefixes, of course, apply to meters, liters, all that as well. But that main unit is 1, or 10 to the power of 0. Kilo is anybody remember how many kilo is? Kilo? 1,000. That's 10 to the power of 3. Mega is a million, 10 to the 6th. Milli is 1,000th, or 10 to the -3, and micro, -6. Nano, of course, would be a billionth, or 10 to the -9. Pico would be 10 to the -12th. Our main metric prefixes. You remember when we talked about, even with meters, we said, the decimeters and deca and hectometers don't get used much. Centimeters gets used in the United States because it's closest to an inch. You go to other countries, they don't use that much either. So if I look at something like 42.3 kilovolts, that is really saying 42.3 times kilo is 10 to the third volts. It's scientific notation or engineering notation. The engineering notation goes along with our metric units and metric prefixes. So we can convert easily. When we go to do a calculation, which is going to be one of our next steps, but we won't do it today, we would have something like 42.3 kilovolts divided by 14.1 mega ohms, and figure out what that current is going to be when you have that voltage applied across that resistance. Well, we have to convert the metric prefixes to their power of 10. Kilo is what power of 10? 10 to the positive 3. That's volts. Mega is what power of 10? 10 to the 6th. Of course, that'll be our ohms. That upside down horseshoe kind of looking thing is ohms. We would divide then. Just like we've done with our other things, you divide the counts. 42.3 divided by 14.1 is actually just 3. And then we divide those powers of 10. 10 to the third divided by 10 to the sixth. What do we do with the powers when we divide? Subtract. So 3 minus 6 is a negative 3. A volt minus an ohm is, or a volt divided by an ohm is an amp. 10 to the negative 3 is milli. So this is 3 milliamps is what our result is that we get there. Make sense? Okay, we've got quite a lengthy assignment here that I have to lay out for you. I apologize for that, but in the big book, there are several pages here. I gotta get closer so I read the old pages. Page 307, exercise 13.2. Page 309, exercise 13.3. Page 313, exercise 13-4. Page 316, exercise 13-5. Those are the operations with our algebraic numbers that we were looking at in the first hour. Then we have page, I lost the page number. Oh, I do have it. Page 211, exercise 6-13A. Page 212, exercise 6-13B, and I missed one here, so it's kind of going to loop back a little bit. Page 205, exercise 6-12A and 6-12B. In the little book, I know, almost done. Units 30 and 31. Give me 6 good minutes working on homework, get started on homework, and then we'll get out of here. I'm sitting right in your way, aren't I, Colton? Sorry. Which way do you want me to lead? Okay. Next time, just move your chair whenever you need to. Do you guys have books here to work on, or? So for those guys that weren't here, I've got a bunch of quizzes here I'll leave for them from the one we got today. Then I got a bunch of quizzes from before break that people were missing. So those will be here in the file as well. What is 307? Yeah, that's definitely there, right? That's definitely on the right page. Yeah, let me see this for a second. So it's 333 is 13.2. That is the correct one, is 333. So that must have been from 2 versions of the book ago. And of course, these other page numbers will just count up from there. Now let me find 613 here. The other numbers look like they're correct. 205 and 211. Look to me right, so those should be good. Thanks, Steve.